The theory of cosmic inflation is an important concept in modern cosmology that aims to explain some of the observed features of the universe's large-scale structure and its current state. It proposes that a very rapid and exponential expansion of space occurred in the early moments of the universe, shortly after the Big Bang. Journey beyond the Big Bang and explore the mind-bending theory of cosmic inflation, where space itself undergoes a rapid, exponential expansion, unraveling the universe's mysteries in just fractions of a second. The universe appears to be remarkably homogeneous, uniform, and isotropic, the same in all directions on large scales. However, without inflation, it's difficult to explain how regions that are currently so distant from each other could have reached thermal equilibrium and be in such close agreement in temperature and structure. Inflation helps to address this problem by suggesting that these regions were much closer together before inflation stretched them out. The universe appears to be almost perfectly flat on large scales, meaning that the geometry of space is very close to being flat. This is unexpected because small deviations from flatness would have grown over time due to the expansion of the universe. Inflation can explain this apparent fine-tuning by suggesting that the rapid expansion during inflation smoothed out any deviations from flatness. Certain regions of the universe are too far apart today to have ever been in casual contact since the Big Bang. Yet, these regions have the same temperature and other properties, which is difficult to explain without some mechanism that allowed them to exchange information in the early universe. Inflation can address this by proposing that these distant regions were actually much closer together before inflation occurred, allowing them to be in contact at some point. Inflation provides a mechanism for the generation of the initial density fluctuations that eventually led to the formation of galaxies, galaxy clusters, and other large-scale structures we see in the universe today. Quantum fluctuations during the inflationary period could have been stretched by the rapid expansion to become the seeds for these structures. The cosmic microwave background radiation is the afterglow of the Big Bang and is nearly uniform in temperature across the sky. Inflation can explain the uniformity and the small fluctuations observed in the CMB by suggesting that these patterns were imprinted during the inflationary epoch. Before we move on, support us by hitting subscribe and the bell icon to get notified when we post new videos. Now, let's get back to our topic. Some models of inflation propose different mechanisms for the underlying physics driving inflation, and researchers continue to explore these ideas through observations, theoretical models, and experiments like those conducted at the Large Hadron Collider (LHC). The evolution of the universe is a complex and fascinating subject studied within the field of cosmology. It involves tracing the history of the universe from its earliest moments to its current state, as well as predicting its future trajectory. The prevailing theory of cosmic evolution is known as the Big Bang theory, which describes the universe's origin, expansion, and development over time. After inflation, the universe continued to expand and cool. Around a few minutes after the Big Bang, the conditions were right for the formation of the lightest elements, such as hydrogen, helium, and traces of lithium and beryllium. This process is known as Big Bang nucleosynthesis and is responsible for the creation of the primordial elements that constitute a significant portion of the universe's matter today. Over the course of millions to billions of years, gravity played a key role in putting matter together into structures. Small density fluctuations imprinted during inflation grew over time, forming clumps of matter that eventually became galaxies, galaxy clusters, and cosmic filaments. Dark matter, which doesn't interact through electromagnetic forces, also played a critical role in the process by providing the gravitational scaffolding for structure formation. For several hundred million years after the Big Bang, the universe entered a phase known as the Dark Ages. During this time, matter was clumping together, but stars and galaxies had not yet formed. Eventually, the first stars ignited, releasing light and ionizing radiation that gradually cleared away the neutral hydrogen gas that had dominated the universe. This period of reionization marked a transition to a more transparent and ionized universe. As the universe continued to evolve, galaxies formed from the gravitational collapse of gas and dust clouds. Within these galaxies, stars ignited, producing heavy elements through nuclear fusion. These stars went through life cycles, some exploding as supernovae and scattered these heavy elements into space. This enriched the interstellar medium and set the stage for the formation of subsequent generations of stars and planetary systems. Throughout its history, the universe has been expanding with galaxies moving away from each other. This expansion was discovered through the observation of galaxies, redshifts, indicating that they are moving away from us. The metric expansion of space itself is a fundamental aspect of the universe's evolution. Around the turn of the 21st century, observations of distant supernovae indicated that the expansion of the universe was actually accelerating, contrary to the expectations based on gravitational attraction alone. Depending on the overall density of the universe and the strength of dark energy, several scenarios have been proposed, including the Big Freeze, where the universe continues to expand and cool, the Big Crunch, where the universe contracts back together, and the Big Rip, where dark energy becomes so dominant that it tears apart galaxies, stars, and even atoms. Astrophysics is a branch of astronomy that focuses on the application of the principles of physics to understand the behavior, properties, and interactions of celestial bodies and the universe as a whole. It seeks to explain the fundamental processes and phenomena that govern the behavior of stars, galaxies, black holes, planets, and other cosmic objects. Astrophysicists use a combination of theoretical models, observations, and experiments to unravel the mysteries of the cosmos. Stellar astrophysics studies the life cycles, structure, and behavior of stars. It delves into processes like nuclear fusion, which power stars, and explores their evolution from birth to death, including the formation of black holes and neutron stars. High-energy astrophysics involves the study of energetic processes and phenomena in the universe, including cosmic rays, high-energy particles, and extreme environments like supernovae, pulsars, and black holes. X-ray and gamma-ray observations provide insights into these extreme cosmic events. While closely related to astronomy, planetary science examines the properties, atmospheres, surfaces, and interiors of planets, moons, asteroids, and comets. It also explores the possibility of habitability and the search for extraterrestrial life. The study of black holes and the detection of gravitational waves, ripples in space-time predicted by Einstein's theory of general relativity, has opened up new avenues for understanding the universe's most extreme events and testing fundamental physics. Astrophysicists use various telescopes and instruments across the electromagnetic spectrum, from radio waves to gamma rays, to observe cosmic phenomena. Advancement in technology, such as space telescopes and interferometers, have revolutionized our understanding of the universe. Astrophysics is an ever-evolving field that pushes the boundaries of human knowledge and deepens our understanding of the universe's underlying physical laws. It often intersects with particle physics, cosmology, and theoretical physics, contributing to our broader understanding of the fundamental nature of reality. Cosmic expansion refers to the phenomenon where the space between galaxies and other celestial objects is increasing over time. Imagine the universe as a balloon being inflated. As the balloon expands, the dots drawn on its surface, representing galaxies, move away from each other. Not because the dots themselves are moving, but because the space between them is increasing. One of the key pieces of evidence for cosmic expansion is the observation of redshift in the light from distant galaxies. When light from an object moves away from an observer, its wavelength becomes longer, shifting towards the red end of the electromagnetic spectrum. This is known as redshift. The greater the redshift of a galaxy, the faster it is receding from us. American astronomer Edwin Hubble discovered a linear relationship between the distance to galaxies and their redshifts. This relationship, known as Hubble's law, suggests that the universe is expanding uniformly, with more distant galaxies receding faster. So that's it. Please like, share, and comment your thoughts below if you liked this video. Remember to subscribe to see our next video. Stay safe, and we will be back soon with another video.